So I wanted to start out with this slide. What is 2 plus 2? Like this is baby math for you guys, right? You probably did this in preschool or kindergarten. Who can tell me what 2 plus 2 is? Just shout it out.
4.
It's 4, right? Like everybody knows that it's 4. If I have 2 apples, and then I'm given another 2 apples, those 2 apples plus the 2 apples I'm given, it's 4 apples, right? But when I ask you in physics what 2 plus 2 is, I have to say the answer is it depends. And it's going to depend on whether something is a scalar or whether it's a vector. All right? Remember I told you that this part of physics for the rest of this week and next week, this is math stuff, right? But it's useful math. Not that all math isn't useful, it's all useful. But it's useful math for us. It's useful math for physics that you just need to know. So let's talk about this for 1 second. Vectors versus scalars. Now, you may or may not have heard those words before, right? Let's attack scalars first. Scalar math is what you've done since you were really little. Okay, when you learned how to add, you learned how to add scalars. When you learned how to subtract, you learned how to subtract scalars. So pretty much all of your math is with scalars. Scalars are quantities, you guys, that only have magnitude. And a quantity is anything that I can measure, anything that I can calculate, right? Distance is a quantity. Speed is a quantity. The number of apples I have is a quantity. So scalars, they are quantities, okay, that only have magnitude. So like the number of apples in that bowl, that would represent a scalar. A scalar could be a number of things. It could be, the distance that you've traveled. It could be how fast you're moving. So hopefully that makes sense. And when I throw out a number, or you guys automatically, your brain automatically assumes it's a scalar. Whether you've heard that word or not, like that's what you're used to. That's how we've done math up till this point. Okay? Vectors are something that's different. When you guys did your treasure map yesterday, you actually made vector maps. All right? So vectors, they're quantities that have magnitude and direction. So let's say that I gave an instruction for someone on my treasure map, and I said, walk 30 meters east. What I did is I gave them a vector. All right? I told them to walk 30 meters, which is the magnitude part, and then I told them to go east, which is the direction part. So anytime you add direction, you now have a vector instead of a scalar. For all of you who like Despicable Me, you probably already knew what a vector was, right? Because Victor commits crimes with magnitude and direction, and he calls himself Vector. I don't know if you remember that. So that is a mathematical term. Vectors have magnitude and direction. Now, just as a review, just to make sure you got it, scalars only have magnitude, vectors, magnitude, and direction. So normally at this point, I would just ask you guys to come up with lists of scalars and vectors. But in this kind of environment, sometimes it's hard to talk or put yourself out there. So I'm just going to put a list up, if you don't mind. So here are some vector versus scalar quantities. All right. Now, there are plenty of things that could have a scalar and a vector equivalent to each other. The very first one is speed. So let's look at speed and velocity. These two things are equivalent to each other. Speed, because it's a scalar, because it only has magnitude, this is just a measure of how fast you're going. So speed is how fast you're going. velocity is how fast you're going and the direction that you're traveling in. So if let's say that we're driving somewhere, and I'm the navigator, so I'm sitting in the passenger seat, and I ask you how fast you're going. If you tell me 30 miles per hour, you've told me your speed. But if you're worried about me and the directions with the map, if you tell me, hey, I'm going east 30 miles per hour, then you've told me your velocity. Okay, so velocity is a vector. It has direction. Speed is a scalar. It only has magnitude. So I want you to think about the consequences of this for a second, why this is important to us. All right? So let's take a little detour for 1 second and remember what acceleration is. Remember that acceleration was the change in velocity. And I told you that we were going to pretend for the moment like velocity and speed were the same thing, even though they were different. So anytime I change my velocity, I'm accelerating. If I slow down, am I accelerating? Someone shout it out.
Yes.
Yes, resounding yes, because I'm changing my velocity. If I speed up, am I accelerating?
Yes.
Yes, of course. So if I slow down, I'm accelerating because my velocity is changing. If I speed up, I'm accelerating because my velocity is changing. So if I'm driving a car, I can hit the brake or I can hit the gas. Now, if I have my cruise control on in the car, that means that my speed is constant. My speed is not changing, right? Because the cruise control keeps me going at a constant speed. Can I accelerate? Can I cause the car to accelerate without hitting the brake or the gas on cruise control?
No.
So that's what that's the answer that everyone would give, right, from the last unit, and it's a perfectly fine answer. But now that we know that velocity is a vector, right? So we know velocity is a vector, and we know that if I change my velocity, I'm accelerating. Vectors have direction, right? So if I'm going at the exact same speed, cruise control, and I turn my wheel, am I changing my velocity?
Yes.
Yes, I am, you guys. And so even though my speed is constant, if I change my direction, I'm changing my velocity and I'm accelerating. You guys actually all know this, right? Sometimes you fake yourselves out into thinking you don't know things that you do know. Because, and this is something that we're going to talk about in the next unit, any acceleration has a force associated with it. If you're going down the highway like super fast, and the person you're driving with is supposed to be giving you directions, and they tell you like, hey, that's our exit right there, right now, you got to turn. And you do one of those like, where you're like going super fast, making a super fast turn. Don't you feel like you're getting pulled out of the car? Can't you feel a force acting on you?
Mm-hmm.
Yeah, you can, right? Even if you haven't hit the gas or brake, that's because you're accelerating. And why are you accelerating? You're accelerating because your velocity is changing, your direction is changing. All right? So just that's one of the reasons why vectors are important. Now, here's another example of a scalar and its vector equivalent. So distance is just how far you've moved. Just how far you've moved from your starting point. Displacement, this is how far you've moved and what direction you've moved in. So basically, you guys, when you did your treasure maps, you made displacement maps. You made vector maps. You told someone, you didn't tell someone, walk 10 paces, somersault 3 times, skip 4 times, right? You didn't tell them that because they would never have even remotely ended up where you wanted them to end up. What you told them is you said, like, face north, walk 10 paces, turn to your right, somersault 3 times. So you were giving them direction and you were giving them distance. So displacement, that's a vector. that's direction and distance. Okay, distance is just the magnitude part. It's just how far you've moved. Displacement, how far you've moved, and what direction you moved in. So like, let's say you were in track, and I asked you what race you ran. You might say the 100 meters. You're just giving me distance. If you say I run 100 meters east, well, then you're giving me displacement. That would be weird. You probably wouldn't tell me that, right? But if you did, that would be displacement. Distance is just how far. Displacement is how far and what direction. Mass and weight are kind of equivalents to each other. Mass, this is a scalar, all right? For mass, it's just, I know you guys remember this from chemistry, it's just how much matter is inside of you, or inside of an object, okay? And we measure mass in what? In chemistry, we measured it in what? Anybody remember? Starts with the G. What was it?
Grams.
Grams, right? So in chemistry, you guys measure it in grams. Now for physics, because we're using bigger objects, we'll always use kilograms. And you guys have a kind of a clear idea of how much mass is in a kilogram, especially if you go to the weight room. Because in the weight room, the big plates, they're stamped with their mass. They're stamped as 20 kilos, right? Now, most of us don't think of those plates as 20 kilograms. Most of us think of those plates as 45 pounds, right? You guys, pounds is weight, and weight is a vector. So mass is just how much stuff is in something, but weight is a vector. Why is it a vector? What direction is involved in your weight?
Going up, pushing up.
Oh, okay. Well, so you're thinking of like the force that the ground is pushing on you, right?
Right.
But your weight is actually the force of you being pulled into the center of the earth. Which, I mean, hopefully that makes sense to everybody. So your weight is always, the direction of your weight is towards the center of the earth. All right? Unless you're on another planet, then it's towards the center of that planet. Okay? And your weight and mass are related, but it's only because the acceleration of gravity is always the same on planet Earth. And we'll get into this more later in the year. But mass doesn't change, weight can, depending on gravity. Okay? Then a few other examples of scalars: time, area, volume. Like, I would never say it was 2 o'clock going southeast at 45 degrees. That's kind of silly. These three things, they don't have direction. They can't have direction. Weight, acceleration, force, those are always in a specific direction. Weight points down. Acceleration, you're always accelerating in a direction. Force, you're always pushing or pulling something in a specific direction. So vectors, magnitude, direction; scalars, magnitude. So I know I kind of beat this into the ground, but everybody understands the difference between the two, right? I'm gonna take that to be a yes for everyone, because I didn't hear any complaints. So now this is why 2 plus 2 doesn't always equal 4, right? When I'm looking at vectors, I can't just take the scalar part. I can't take the magnitude part and add them together when I add vectors. So vector addition always involves me taking one single vector that would replace all the other vectors that I have. So I want you to think about your treasure maps for a second. You made treasure maps that were 10 to 15 steps long. Okay? Now when we do this in school, you guys, almost nobody ends up where they're supposed to end up, because we have the run of the school, we have the run of outside, and because it's over such a big area, standard units and those things are a problem. So most of you probably ended up where you were supposed to in relation to the starting point, just because you were kind of contained to a smaller area. But when I give you the run of the school, instead of taking 10 steps, lots of people have their partners take 50 steps, right? Well, your 50 steps and my 50 steps, that could be a really big difference between the two distances. So that's just a note that you always have to use standard distances, all right? But I want you to think about this. So you made your map. You had 10 or 15 steps in it. You started in one spot. The person ended in another spot. Could you have replaced those 10 or 15 steps with just one step, one set of instructions?
Yeah.
Yeah, you could have, right? That one step that you would have replaced all the other ones for your map, that is what we call the vector sum. So when we add vectors together, the one vector or the one instruction that could replace all of the other ones, that is the vector sum. So I'm going to give you an example of how 2 plus 2 will not equal 4. All right? And this is my example. So I want to know what the resulting displacement is if you walk 10 meters east from your starting point and then walk 10 meters west. So I have this person, and she's walking, say, to school, all right? And she's going to walk 10 meters east. So on my screen, east points to the right. Then she stops, all right? She turns around, and she's going to walk back 10 meters west. How far did she end up from where she started? It's not a tough question. What?
Same spot.
Same spot, right? So the vector sum of 10 meters east and 10 meters west, that vector sum would be 0. It would be 0 meters. Now, the scalar sum would be 20, right? If I asked you how far did she actually walk, she walked 20 meters. But so if I was your gym teacher, let's say, and I asked you how much exercise you got in, you would say, well, I got in 20 meters of exercise, right? But if I'm your physics teacher and I say, what was the vector sum? Like, how far did you end up from where you started? You would say 0. So anytime, you guys, when you're adding vectors, I'm going to give you a clue right now. You could write this down. The smallest the vector sum can be is the scalar difference between the numbers. So 10 minus 10 equals 0. That's the smallest the resultant could be. What do you think the biggest the resultant could be? So if the small... I'm sorry, what?
Could you repeat the first thing you said?
Yeah. So whenever I'm adding vectors, the smallest possible answer that I could get when I add them is the scalar difference, or the subtraction of the magnitudes, right? So if I were to take 10 minus 10, so I just take the two magnitudes and I subtract them, that's the smallest possible answer I could get for the sum of the two vectors. That would be 0. So what would be the biggest it could possibly be? I'll give you a hint. What if she walked... Wait, I'm sorry, say that again?
Wouldn't it be like 20?
It would exactly be 20. Because if I said she walked 10 meters east, and then she walked another 10 meters east, didn't she end up 20 meters from her starting spot? So the biggest would be if I took the magnitudes and I added them. So if you add the magnitudes together, that's the biggest scalar sum. If you subtract the magnitudes, that's the smallest scalar sum. Could it be a number in between those two things? The answer to that is yes. So if I can rotate this, I can rotate it here. So let's say that instead of going in a straight line, right? Let's say this was her treasure map. She walked 10 meters east and then turned 45 degrees and walked down here. How far did she end up from where she started? Isn't that somewhere in between 0 and 20? You guys see that?
Yes.
Yeah, okay. So it could be basically the vector sum, you guys, can be anything between 0 and 20. It could be anything between the difference between the magnitudes and the sum of the magnitudes. All right, that will be the vector sum. Now the vector sum is something that we call the resultant. The resultant is the one vector that could replace all other vectors. So let me go to the next slide here. Well, first of all, before we go, does anybody have questions on this so far?
Wait, is it, so if it was 5 plus 5, that would be the biggest, vector?
Right, so
Biggest
yeah, so let's say that I asked you to walk for your treasure map. Let's say that instruction 1 was walk 5 meters, and instruction 2 is to walk another 5 meters. So the furthest you could end up from where you started was 10 meters, okay? The closest you could end up is 0, and it would all depend on the directions that I gave you in between, right? So if I told you walk 5 meters, stop, or walk 5 meters north, stop, walk another 5 meters north, you'll end up 10 meters from where you started. If I tell you walk 5 meters north, stop, walk 5 meters south, stop, you'll be right back at your starting point,
okay.
right? But if I told you walk 5 meters north, stop, and walk 5 meters west, you'll be somewhere in between 0 and 10 meters from your starting point, right?
Yeah.
Right, so that's a good way to check, you guys, to make sure that you got an answer right. It has to be somewhere in between the difference and the sum of the magnitudes. And we're gonna do a problem, an actual like problem, okay? Now, there's different ways that you can figure out what this resultant vector is. All right. The first way is you could actually draw these. So I could get a ruler. I'm going to pull out a ruler. And then I'm going to draw this out. This is my treasure map. So I have a person. They're walking a treasure map, and they're told to walk 3 meters north. Okay. So I take my ruler. I'm going to move it up. I'm going to use this scale right here. I'm going to pretend that each one of these is 1 meter. So there's 1 meter, 2 meter, 3 meters. So there's my first vector. So I'm going to walk 3 meters north. Then I'm told, now you have to walk 4 meters east. Okay, well, so now I'll grab my ruler again. I'll use it to draw it out. And there's 1, 2, 3, 4. Okay, 4 meters east. So I drew those to scale. And I want to know, what is the resultant displacement? So the resultant displacement, that's the vector sum. That's how far we ended up from where we started. Now in this case, you guys, we did 3 and 4. So the smallest the resultant could be is 1. The biggest it could be is 7. It's got to be somewhere in between there. All right. Now, how do we figure it out? Well, we go to the starting point where we started our treasure map, and then we're going to draw a line straight to the ending point where we would have ended our treasure map. This right here, that line, that is something we call the resultant, and that is the vector sum. So when I add these two vectors, the resultant is the answer. This is the vector sum right here. Now, how would I figure out how long that is? Well, I have my ruler. So I'm going to take my ruler and put it there. And then of course I have to move my ruler so that it's going to line up. And if I put it from start to finish, I look at this 1, 2, 3, 4, 5. So this is going to be my answer. My answer is going to be 5 meters. Now, let me ask you this. Can this be the whole answer if it's a vector? Vectors have what and what? They have two things.
Magnitude and direction.
Magnitude and direction. Okay, 5 meters, that's only magnitude. I need the direction too. So I would have to pull out my protractor. Here it is. I would pull out my protractor. Oops. Trying to move it. And I would put it right here. And I would say, okay, we'll use this for now. Or actually, we'll use this. It's 30, let's say 36. So 5 meters at 36 degrees. And that's because we're measuring, because we're measuring this angle, okay? And we're going to talk about how to label these. But I'm going to write it down here because it's getting messy. So that's 5 meters. And this is a little at symbol, you guys. I'm really bad at drawing them on these things. That's like the at in your email address. So 5 meters at 36 degrees. And if this was east, that is going to be north of east. Because I would have started out pointing in the east direction. I had to turn 36 degrees north of that, and then I walked that line. So this would be my answer. I'm sorry.
Just east.
I'm sorry. Can you say that again?
Could we just say like northeast?
So the answer to that, the short answer to that is no. I know you guys want to say it, but because here's the problem, right? I could either state this one of two ways. I could either say that you could walk 5 meters, 36 degrees north of east. Oops. What did I just do? Hold on. Trying to get rid of this. Or I could say I walk 5 meters. Oops, I accidentally. At 54 degrees east of north. And this is something we're going to get into more tomorrow. I don't want to get too into the weeds today because I know this is already a little bit hard. Here, I'm going to get rid of this. I'm going to pull this back up again for you guys. So these are my vectors. So if I use this angle, that's still northeast, right? This angle is still northeast. But if I tell someone to go 36 degrees north of east and 54 degrees north of east, those are the same thing. If I just say go 36 or 54 degrees northeast, those are, you won't end up in the right spot maybe. You have a 50-50 chance ending up in the right spot. And don't get too hung up on the direction yet. Don't get too hung up on it. We're going to go over it. For right now, just know that I have to have direction and I have to have magnitude. Okay? So when I added 3 meters north and 4 meters east, it ended up being 5 meters, 36 degrees north of east. So that is between 1 and 7. And so everything worked out. Everything worked out for us. Let me just tell you right now that if you want to solve a problem graphically like we just did, you don't actually have to use your calculators, right? You always have to draw them to the same scale. And you always draw the vectors what we call head to tail. So what that means is this. Let's bring these back up. So when I draw a vector head to tail, it means that I always draw one. I always begin one at the end of the other. So there's the head of the vector, there's the tail, and then I put the beginning, which is the head of the vector, on the tail of the other one. So I always do the instructions one after the other. So it's this kind of stuff, you guys, is hard for me to teach without seeing your faces and gauging your reactions. Is it making sense so far, with the exception of the angle part? Or the direction, I should say, the north of east, all that. Is the rest of it making sense?
Yes.
Okay, all right. So now, there's another thing, another question I have for you, all right? And that is, if you were going to do your treasure maps, let's say you had submitted them to me. You did them in a wide open space, right? If I had taken all of your instructions and I jumbled them up, just completely mixed them up. So if you said if maybe your map said walk, for the sake of just ease, let's say you said walk 3 meters north, walk 4 meters east. If I cut those two instructions and reversed them, and I said walk 4 meters east and 3 meters north, would you end up in the same place?
No.
Are you sure about that? So,
Maybe.
right, if I took the same starting point and I had you go 4 meters east and then I had you go 3 meters north, you actually do end up in the same starting spot. I know it seems weird, you guys, but I could have taken your maps, jumbled up every single instruction, and assuming that the maps were right and the people followed them right, they would have ended up in the exact same spot. Okay, so this is exactly like scalar addition. It actually doesn't matter. If I have 3 plus 4, that'll give me the same answer as 4 plus 3, doesn't it?
Mm-hmm.
Yeah, I know you guys know that's true. So that's called the commutative principle or property, whatever. It applies to vectors. It applies to vectors just like it applies to scalars. It's exactly the same. So order doesn't matter. You can do things any way you want. Because if I do instruction 1 and then instruction 2, I end up in the same spot. Or if I do instruction 2 to start off with and then instruction 1, I still end up in the same spot. Now, a lot of people like drawing these. I personally just like to use math. All right? So there's a way to use math, and you guys are good at it. This is math that pretty much all of you know and you're good at. It does involve a little bit of trig, okay? But I can figure out the length of this side by using the Pythagorean theorem, right? So I know that this side is 3 meters. I know that this side is 4 meters. What equation would I use to figure out the length of that side, or the hypotenuse?
A squared plus B squared equals C squared.
That's exactly right. So I have A squared plus B squared equals C squared. Okay, so I'll have 3 squared plus 4 squared equals C squared. And 3 squared is 9, 4 squared is 16. Add those together, it'll be 25. I want to get rid of the squared on the C squared. I take the square root of both sides, and I end up with C equals 5. Okay? So I know that this is going to be 5 meters. That's the exact same answer we got by drawing it out to scale. And just in case you guys didn't figure it out, I picked a 3, 4, 5 triangle on purpose because I knew that it would come out to whole numbers, right? Now, this part, I need to get the angle again, right? So I know that this interior angle right here, I'm pretty sure we said that was 54.4. I can never remember exactly what the angles are. 30, 60, 90, that's what it is. So anyway, if we want to find this, we use our trig function. So we're going to use SOHCAHTOA. Which trig function do you guys like the best? Sine, cosine, or tangent?
Tangent.
Tangent? Okay. So tangent, that's the TOA part. Tangent of the angle is the opposite over the hypotenuse. Oh wait, I'm sorry. Opposite over adjacent. I got a momentary brain cramp. So tangent, opposite over adjacent. And so we're going to stick our numbers in here, right? Tangent of the angle is the opposite side of the angle, which is 4, divided by the adjacent side, which is 3. Plug that in my calculator, and it'll be 1.33. Now, I want to get the angle. So in my calculator, I have to hit inverse tangent. And if you have one of the TI calculators, you guys, you have to go into where it says trig functions, and it says tangent with the little dash next to it. So if I do the inverse tangent of 4/3, what do I get? Can someone shout it out? If you're using, by the way, I don't know if you guys know this or not. I'll try to hold up my calculator. If you're using your cell phone and you turn it to the side, I don't know if everybody knows that, then it becomes a scientific calculator. So you could even do it on your cell phone. So you would put 1.33 and then second tan. Anybody? $53 degrees. So that would be 53 degrees east and north. And actually, when we measured it to be 54 with our protractor. So we were pretty close, right? Not exactly perfect. So the magnitude part, 5 meters. The angle part, 53 degrees.
Wait, how do you put it in the calculator again?
So it totally depends on what calculator you have, and some of you were given brand new calculators by math, and I actually don't understand how to use the trig functions. We haven't been able to figure that out because I haven't seen one. So
I have like a regular one.
So you have a regular calculator? So if you have a regular, if you have a regular solar powered calculator, which by the way, that's all you guys need for this class, all right? You would punch in 1.33. And then in the upper left-hand corner, there's a second button. You would hit second, and you would hit tangent, and then enter. And it'll give you the answer. Now, you may have to hit second tan, and then 1.33 enter. All the calculators are slightly different. Like on the cell phone, on the cell phone, you guys, if you can kind of see this, I have to put in the number first, and then hit second, and then hit tan. You can't. It's coming in and out. On your calculator, you may have to do the opposite. And then you guys know right now with your computers, you can always use Desmos. I think you've used them in math before, right?
Mm-hmm.
Yeah. So that's something that we can work out together. But that's vector basics.